Hello, this is Geometry, Section 9.1, Translations. Here are our notes for today. If you reflect, rotate, or translate a figure, this is called a transformation, and these are some of the rules. The new figure is called the image. The original figure is called the pre-image. So the pre-image happens first, and the image happens second. A transformation, the action of moving the pre-image onto an image. And this can be done through reflections, rotations, and translations. We are going to learn about 3 types of transformations and combinations of these. The first picture is a reflection, where F is reflected over the line. So the blue is the pre-image, and the red F is the image. Same goes for the rotation. Blue is pre-image, red is image, and translation is a slide. A rigid motion, a transformation that preserves distance and angle measure. Distance and angle measure. So think about the figures as being congruent. Notice the F's above have not changed size and they have not changed shape. Look at the following pairs of figures. Does the transformation appear to be a rigid motion? Explain. Notice in picture number 1, the pre-image is in black and the image is in blue. The pre-image is smaller and it gets bigger. Do you remember what the definition of a rigid motion is? A transformation that preserves distance and angle measure. So in figure number 1, I would say no, distance is not preserved. It looks like they're all still right angles, but because distance is not preserved, it's a no. Number 2, they all look the same length. The angles look good. So I would say, yes, distance and angle measure are preserved. Number 3, yes, distance and angle measure are preserved. In our book, the pre-image is always black and the image is always blue. If you're naming the pre-image as A, the image would be read A prime, and that little symbol or apostrophe is the prime symbol. So down here I would say triangle JKQ is mapped onto triangle J prime, K prime, Q prime. Triangle JKQ maps onto. That's the arrow means maps onto. And notice how when we have a triangle you use the triangle symbol. Please turn the page. In the diagram, EFGH is mapped onto E prime, F prime, G prime, and H prime. That statement is very helpful to us. That helps us pick out the orientation, figure out which matches and which points are reflections of each other, or images and pre-images. So looking at question A, what are the images of F and H? So the F is here, F is mapped onto F prime. H, angle H is here, and it is mapped onto H prime. Take a look at my notation. Question B, what are the pairs of corresponding sides? So I named the sides and said what they are mapped onto. So I started EF is mapped onto E prime and F prime. FG is mapped onto F prime, G prime. Notice I still have the segment bar on top of there. GH is mapped onto G prime, H prime, and HE is mapped onto H prime, E prime. If you need to pause the video to write down some of the answers, please do that whenever you need. In the next picture, it is not so obvious which points match up. What are the images of angle I and point D? So in the diagram, triangle NID is mapped onto triangle SUP. This is very important to look at in this example. So one of the things you could do is look at your statement and make some markings on your picture. N is first and S is first. So I'm going to put markings on them. So N maps on to S. I maps on to U. And D maps on to P. Now that I have it color-coded, it's easier for me to tell what maps onto what. Whereas on the picture above, you just put the prime symbol next to its match, or corresponding parts if you want to talk mathematically. So what are the images of I? I is mapped onto what? You got it, angle U. And point D is mapped onto, oh, thanks for participating, point P. Part B, what are the pairs of corresponding sides? So what I did was I started by naming all three sides and then looked for the corresponding colors. So NI, red to green, matches from S to U. I to D, green to blue, matches from U to P. D to N maps from P to S. And technically I could have S to P, but I like to keep the color coding in order. So here's the vocab word for today. A translation is a transformation that moves a figure up or down and left or right. So slang would be to do a slide, where you can slide the figure. And here's the notation. Capital T of triangle ABC is mapped onto triangle A prime, B prime, C prime. So down here on the bottom in my red box are the notations for translations. So you might want to add the words coordinate notation to that, where we write our notation in terms of coordinates from the coordinate plane. So point XY is mapped onto X plus 4, comma, Y minus 2. So we would move every point forward 4, and minus 2 would take us down 2 on the coordinate plane. So that is coordinate notation. Vector notation is using a vector. So when I put these bars in here, that's a vector, the way that you would write a vector. So the first point says forward 4, and the second coordinate means to go back or down 2. So forward 4, down 2, same thing that our coordinate notation says. So again, a capital T and then a mini, or in small subscript, V, comma, 2. So in both of these examples, what is happening is we're taking the black pre-image and moving it onto the blue image. So X is the left-right movement, so I go forward 4, and then Y is the up and down movement, so I'm going down 2. So forward 4, down 2. So let's try a translation. What are the vertices of the translation -2, 5 of triangle PQR? Graph the image. So this is the pre-image, and we need to move this according to our vector notation. So the first number takes us forward or backwards, and the second number takes us up or down. So let's go forward backwards first. So I'm going to take each point, and I'm going to go backwards 2. So 1, 2, make a mark, 1, 2, make a mark, 1, 2, make a mark. I connect my dots, and there is my image. If I do it algebraically, I can look at my points. I wrote the coordinates of every point. And now from every x value, I'm going to subtract 2. And then from every y value, I'm going to subtract 5. So 2 minus 2 is 0. 1 minus 5 is -4. So if I double check, P prime, starting at the origin, is 0 backwards 4. Excuse me, 0 up 4. Have you figured out what I forgot to do? You got it. I only did the blue translation. I need to keep translating my picture so that I can reflect the y coordinate. So now if I look at my coordinates, the 0, -4 goes down to this red point P prime. So if I continue with the algebra or math, 3 minus 2 gives me 1, 3 minus 5 for -2, and our last coordinate would be -3, -2. So if you match that up, those points will match with my black triangle, which is my solution. Also notice I did put labels on my answer. So this black triangle with blue dots is like me showing my step of work, so that's halfway there with the x, and then if I apply the y vector, then it ends up down here. Remember, pause the video if you need more time. So let's go through some application questions. We know that a rigid motion is a transformation in which a figure's size and shape are not altered, although positioning can be altered. Given this, what is the definition of a non-rigid transformation? A non-rigid transformation is a transformation where a figure's size and/or shape may be altered. You are sitting across the table from a friend and you agree to share a triangular grilled cheese sandwich. You spin the plate to your friend. Part A. Which transformation did you perform on the grilled cheese sandwich? So here's what your plate might look like, where you're sitting down here and your friend is sitting up here. And you need to spin your plate towards your friend. So maybe it looks like this. So I did spin the plate. I guess it just doesn't look like it. So let me add some decorations so that you can see what's happening with the whole plate. So there, the plate moves too. Part A. Which transformations did you perform on the grilled cheese sandwich? You are picking from reflection, translation, and rotation. Well, a translation and rotation. I definitely rotated it, but maybe the table is bigger than just our plate, so I probably had to slide the plate to my friend also to get it closer to her so she could eat it. Our plate probably is not the same size as the table. And then part B, is this a rigid transformation? Yes. The sandwich only moved location and orientation. It did not change shape or size during the transformation. Which of the following is a rigid transformation? Mark all that apply. So what I'm going to do is just put a check mark next to each dot. So why don't you pause the video and see what you get. Dribbling a basketball. The ball stays the same size and shape, so that would be yes, it is rigid. Flipping the page in the book. Yes, the book does not change shape. Inflating a balloon. No, it gets bigger. Knocking over an empty cup. The cup preserves angle and side length. Cutting a piece of paper. No, it's going to get smaller. Dropping your cell phone. Yes, because hopefully it doesn't break and get smaller. Flying a paper airplane. Yes, it's going to maintain its shape and size. A plant growing over a week's time. No, it's going to get bigger. So these are some real-world applications of rigid transformations. This concludes my video on translations.